3.3, last time we started this section, we were taking a look at increasing and decreasing functions, and we talked about the first derivative test. We did a couple of examples, just to remind you. And so our examples here asked us specifically to find increasing and decreasing. The way that we did that is we found where the derivative was either equal to 0 or where the derivative doesn't exist, and those are our critical points. We created a number line, okay? So we set the derivative equal to 0 solved. We created a number line with those locations marked on the number line, and then we chose test points within each interval. And those test points are the same, whether you pick the same test point I do or not, as long as they're in the same interval, we'll get the same sign, and that sign tells us if it's increasing or decreasing. Positive means it's increasing, negative means it's decreasing. So we did a couple of examples of that. So our directions are going to change for problem number 3. There's A, B, C, D parts, but most of them are things we've already done. There's a new piece at the beginning, at the end that we haven't. It says find the critical numbers of f. We've done that before. Part B, it says to find the open intervals on which the function's increasing and decreasing. That was our last two problems. C says apply the first derivative test to identify relative extrema. So if we'd been asked to do that on this graph, or this equation, what we would have done then is we would have said, hey, look, negative means it's decreasing, positive means it's increasing. Right here, it's a minimum, okay? So that's the only thing that's new on that part. And then part D is simply to graph it to make sure that it makes sense with what you expect it to happen. Sound good? So very little different than what we've actually already done, just a couple additional steps at the end. So on this one, I started off with something that you are very familiar with. What is this an equation of? Parabola. How does a parabola open? It's a parabola opening downward. So we're expecting that it goes, well, that's terrible. Wow. That it goes from increasing to decreasing, and when it changes directions, we have a maximum. That's our expectation, right? And when we graph it at the end, that's exactly what it's going to look like, set somewhere on the XY plane. Make sense? Okay, so the process is all the same as last time. So part A is to find critical numbers. So critical numbers means I do what? Take the derivative. Okay, so Kaylee, what's the derivative? Negative 4x plus 4. Okay, so Kaylee told me the first step. Somebody told me the second step. What do I do next after I've taken the derivative? Thank you, Jeffrey. I set it equal to 0. And if I set this equal to 0, what will I get for x? 1. Good. So that's step 1. That's part A. That's my critical number. Step B, all right, part B, whatever. It says I need to figure out where it's increasing, decreasing. That's what we did last time with the number line. So we do our number line and we put the critical number on the number line. Okay, now what? Test points, exactly. So Nick, we do test points. Pick me some test points for this one. Wonderful. I love those. 0 and 2 are fantastic test points. Not the only ones, but they're nice ones, especially 0. So if I put the 0 in, and again, we're putting it into the derivative. Whoops, let me do it this part here. So if I put in 0, what do I get? 4, which is positive or negative? Positive. And if I put in 2, what do I get? Negative 4, which is indeed then negative. So that's my sign chart. So let's identify from this sign chart where our function is increasing and where it's decreasing. So on what interval is this function increasing? Fabulous, negative infinity to 1. And remember parentheses. And on what interval is this function decreasing? 1 to infinity. And from what we talked about at the beginning, so far everything is matching up. It was increasing, it was decreasing, just like we expected from what we know about parabolas. Part C says to determine if I have maxes or mins. So even if this weren't a parabola of a function in which we knew exactly what was going, from the sign chart, increasing means I'm going uphill, or positive means I'm increasing going uphill, decreasing means I'm going downhill. So what in the world happens here? It's a maximum. So I have a maximum, and it's occurring at x equal 1. Now, that's not the maximum value itself. So I'm going to actually shift this at x equal 1 over here a little bit. And I'm going to find the maximum value. So how would I find the maximum value? We've actually already talked about this back in 3.1. Right, we put 1 into the original equation. So we do f of 1, not f prime, but f of 1. So if I put 1 into the original equation, that was back up here. Is it 5? Yep, that's what I have written down too. It's 5. So the maximum of 5 at x equal 1. So far, these are my sort of my answers I have. This is the critical number. This is the increasing, decreasing, and this is my statement about maximum and minimum. There's no minimum, right? There's only one location, so there's just one. The last thing is to confirm with your calculator. So go ahead and graph it. Let's make sure that it actually looks like what you expect it to look like. So if you put it into your calculator, do you in fact get the parabola in your mind that we sort of sketched earlier? My sketch on my paper that I have drawn from sometime in the past looks something like that. Is that what yours looks like? So does it in fact go from increasing to decreasing? Yes. Does it in fact have a maximum? Yes. If you just want to shift over there and trace a little bit, does it seem reasonable that the maximum is actually at the ordered pair 1, 5? The answer, of course, is yes. This is what we have going on. Any questions on that one? Okay, so I started with something that was familiar. Did that on purpose, obviously, because we're now going to move into something that's less familiar. Depending on how long it's been, this function may completely be like, I have no idea what that looks like. It's not one we use very often, right? I would not expect you to just be able to pull this out of, oh, it looks like this. We just don't use it much. So when we get to the part D at the end, when we graph it, we're going to be confirming it in a more honest way than we did on the last problem. The last one was sort of just like we just did it because we were supposed to, not because we really needed to, right? All right, so all the steps are the same. Take the derivative, set it equal to 0. That's part A. So what is the derivative of x to the 1/3 plus 1?
1/3 x to the negative 2/3.
Fabulous. And then the plus 1 is going away. So this is my derivative. Now, in terms of setting it equal to 0 and solving, this is not a very pretty way to look at the derivative. So if you were doing the derivative gateway, I'll put a plug in for that. You guys have one more opportunity to pass. If you're still working on getting that done, come see me today between 12 and 1. If that time is the class time you have class, talk to me right after class. Tell me when you can come, and I'll put it on file with a colleague, okay, so you can still take it again. But for what we're doing now, it doesn't really help us to leave it as x to the negative 2/3 like that, right? I mean, like, that's not cool. So we would like to rewrite that with no negative exponent, with no 1/3 or 2/3 exponents either. So how could I rewrite this in a more helpful way?
1 divided by 3 cube root x squared.
That's correct. Okay, so the negative means it goes to the denominator. The power of 2/3, the thirds part makes it a cube root, and the power of 2, then the 2/3 makes it a power of 2. So is everybody good on the rewriting on that part? Is it okay? Okay, so what we're supposed to do is set this equal to 0 or set this equal to does not exist. And those are the two options. The kicker is that if it's equal to 0, or if you try to set it equal to 0, there is no way to do that. And again, we've talked about this before, but as a reminder, in order for a fraction to equal 0, the numerator must be set equal to 0. And this numerator can't equal 0 because it already equals 1. Right? It's just a number. There's no way for that number to turn into 0. However, the other option, of course, is to have this equal, or to try to find where this does not exist. So I realize does not exist is not a number, but just for the purposes of what we're looking for. That's what we're trying to find out, right? We're trying to find out where this does not exist. And at what x value does this not exist? 0. Yeah, at 0. 0 would make the denominator 0. That's no good, right? It's undefined. So this is our critical point, and I only have one again, just like the last time. All right, so part B is the number line part. So I set up a number line with 0 marked on it. So give me some test points. What's a test point before 0? What's a test point after 0? Sure, 1 and negative 1. You're welcome to grab your calculator if you want to do it in your calculator. Remember, we're doing it for this, let me We're doing it for this equation. Because it's 1 and negative 1, it's actually really nice. And not only that, but because the x is squared, 1 and negative 1 both end up being 1 or positive when you square them, right? Okay, so I'm going to get a 1 underneath the cube root. And what's the cube root of 1? 1, right? And then I've got the 3 out in front, so that's 3. So I'm going to end up getting 1/3. And in particular, the part I care about is the sign. What do I get for my sign? Positives. On both of them, right? Yeah, on both. So with this sign chart, I can make decisions about the increasing or decreasing nature of this function. In particular, there's only positives, which means this function is only, what? Only increasing, going upward, right? So this function is only increasing. But it's increasing on 2 separate intervals, because at 0 it doesn't exist. So we can't just say negative infinity to infinity, it's increasing. It's not true. It is not increasing at 0 because it's not defined as 0. So this is increasing from negative infinity to 0, union 0 to infinity. Because at 0 we have a place where the derivative does not exist. Okay? Now, think in terms of the graph going on. Whoops. This means it's going uphill and uphill again. What does that tell you about maxes and mins? There are none, right? In order for there to be a max and min, it has to do increasing, decreasing, or decreasing, increasing, right? It has to change direction, and this does not change direction. So for part C here, there are no local extrema. And you can say no local maxes and mins if you prefer. Extrema just includes both of them. So take your calculator. Take a look at what this graph looks like. I know some of you already did it because I was watching. But go ahead and let your calculator tell you what in the world does this look like. It kind of looks like a sideways tangent, doesn't it? It's like twisted. Or you might think of it looking like an x cubed function on its side. Does your graph give you that kind of a feel to it? Like if you rotated it 90 degrees, you'd have something that looks like cubic function. There's a good reason for that. It's actually the inverse of a cubic function because it's a cube root. So it looks something like this. Does that seem right? My graph is a little bit tainted sideways. So let me see if I can shift it to make sense. Hang on. It's more like this. And what's actually happening at x equals 0 right here in the middle? Any ideas? It's not an asymptote. It's a good guess. There's 3 ways that we can fail to have a derivative. Asymptotes are 1. Holes is another, so we'll say 4 then.
Vertical.
Jumps. Vertical, what was it?
Vertical is just a straight line.
Yeah. Yeah, the tangent line, right? The tangent line is vertical. There is a vertical tangent line here. That's what's actually going on. I have a vertical tangent line. And I made mention before, back when we talked about that, is that we don't see that happen very much. And we don't have it happen very often. We don't deal with functions with vertical tangent lines. This is one that does have one. And that's what's going on there. Very good. All right, next one. Very similar directions. It's trig function. So it says consider the function, but we have an interval 0 to 2 pi because it's a trig function, right? It wants us to find the open intervals in which the function is increasing and decreasing. And B is to apply the first derivative test, and C says to use the graphing utility. And it doesn't have the same part A we had before about finding critical numbers, but like that's part of it, right? Because that's how we do the other pieces. So it's like they're just shortcutting the directions, although they're there. So part A is to find increasing, decreasing. So what is the derivative of x plus 2 sine x? All right, and I'm going to write it in the other order, but you're right. 1 plus 2 cosine of x. Everybody good with that? Fabulous. And then what do? We solve it equal. We set it equal to 0 to solve. Right, exactly. So we're going to move the 1, we're going to move the 2. So we actually have that the cosine of x is equal to what?
-1/2.
-1/2. And as we know with trig functions, in particular, we're working on a full, period of 2 pi, like the entire 2 pi period. We expect most of the time, or we get at least 2 answers, right? So some of you might be tempted, and it's totally fine if you want to do it, to do the inverse cosine in your calculator to tell it to inverse cosine of -1/2. And that's fine, but it'll only give you one of the 2 answers. You still have to come up with the other one on your own. So your calculator is limited in its ability to help you because it will only give you one of the answers that are there, because it actually narrowly focuses its interval smaller than 1 period of a rotation. It focuses in only on half of a period to make that work, just FYI. All right, so let's see if you remember. Cosine. Let's just run through a little bit of remembrance of the unit circle. Where's cosine negative?
2 and 3.
It's negative in 2 and 3. Okay, so these are the quadrants where I'm going to actually find values if you're thinking about unit circle, right? Because I need a negative cosine value. And then I need my cosine to be 1/2 within those quadrants.
Pi over 3s.
So what do you want to say?
It's going to be pi over 3, so is it 2 pi over 3?
So pi over 3 and 2 pi over 3 is what?
No, it's got to be pi over 3, so 2 pi over 3 and 4 pi over 3.
Okay.
I think.
Okay, let me adjust this one. So you're thinking 2 pi over 3 and 4 pi over 3?
Yeah.
Okay, do you agree? I've seen lots of nods. So just as a reminder, because we haven't really talked about unit circle, and I've kind of said, just go look at it online, which, this isn't trig, and so that's like sort of fair. But just to remind you, when you're looking for these functions, the 1/2s and the square root of 3s over 2s are always occurring at either pi over 3 or pi over 6 values. They're either here or they're here, right? And you have to figure out which one it is. So I keep trying to move my screen and I keep pulling up other tools. This particular point is the ordered pair xy, any value is, and the x value is what corresponds to the cosine value. Are you with me? Does everybody remember this from trig? So is the x value here the smaller of the 1/2 and square root of 3 over 2, or is the bigger? Which one is it at this point? And it's the 1/2, right? Because 1/2 is smaller than square root of 3 over 2. And this value of x here has less value than, I need another color, than what I would get if I went over here all the way to here. Are you guys with me? Okay, so just a brief reminder. It is 2 pi over 3 and 4 pi over 3. Okay, so is everybody good with that? Okay, so we are ready to do our number line then. Because this is still now technically part of A. I'm going between 0 and 2 pi, so I don't need my number line to go to infinity, negative infinity. And I need it to have these 2 values marked at 2 pi over 3 and 4 pi over 3. And you're welcome to use values that are nice unit circle values. There's nothing wrong with that. But one of the things we talked about back in section 1 is that if we're plugging the value in just for the purpose of finding positives and negatives, we could also just let our calculator do all of that work for us and use nice whole number values. So for instance, if I'm looking for a test point, what is a nice whole number value between 0 and 2 pi over 3? 1. 1 should work, right? So yeah, that'll work. How about between 2 pi over 3 and 4 pi over 3? 4? I think 4 will work. I know 3 would work. If you're not sure, what you can do is you can actually find a decimal approximation for 2 pi over 3 and a decimal approximation for 4 pi over 3 and just look for a whole number between them. I didn't write down, but I think 4 is okay. And then how about a number between 4 pi over 3 and 2 pi? 5, or even 6 would be okay, right? All right, so we're going to plug these numbers in, but we're plugging them in again. Where? The derivative. We need to plug them into the derivative. So here's my derivative, 1 plus 2 cosine x. And what I want to know, I would do it in the table. I'd put that into y1 in your calculator, and I'd go into the table, and I'd look at 1, 4, and 5. So what is the sign at x equal 1? Positive. What's the sign at x equal to 4? negative, and the sign at x equal to 5, positive. Is everybody good? Okay. So tell me, what do you know? Increasing, decreasing. Where is this function increasing?
0 to 2 pi over 3, 4 pi over 3, 2 pi.
Good job. And it's decreasing then where? 2 pi over 3 to 4 pi over 3. Looks good. Grab your calculator. You already put it in. Well, you put the derivative in, so take that out. Put the original function in. Part C is actually, oh wait, we haven't done the first derivative test. Let me do that real quick first. I was already jumping to part C. Part B, so this is part A. Part B is the first derivative test. So back over here on my sign chart, this is positive, negative, and then positive, right? Increasing, decreasing, increasing is what you said. So what happens at 2 pi over 3? There's a maximum. So we'll find the maximum value in a moment, but there's a maximum, I'll leave a space, at x equals 2 pi over 3. And what's happening over here at 4 pi over 3? There's a minimum there. So there's a minimum at x equals 4 pi over 3. And if you'll take your calculator, because we're going to graph it on part C anyway, put the original equation, x plus 2 sine x, into your calculator. Okay, just put it in. And then you can put it into your table. Is it giving you a weird value? It's a weird graph. Okay. Did you do the table part, Kaylee? Okay, so if we do the table part and we plug in 2 pi over 3, what did you get? I'm sorry. Oh, it's ugly. If it's ugly, we're going to have to talk about how to do it by hand. I think it's ugly. Yeah, it's ugly. Okay, so let's do it by hand real quick. It's a decimal that doesn't look like it repeats because it probably has a square root involved in the answer, or maybe a pi involved in the answer. It's irrational anyway. So let's just go back over here and do them by hand. So if I do the first one, I would have 2 pi. That was not right. 2 pi over 3 plus the sine of 2 pi over 3. So do you know what the sine of 2 pi over 3 is?
2 sine.
Oh, did I write this wrong? Oh, thank you. I'm missing the 2 right in between is what you're telling me. Is that right? Okay, thank you. Man, I've got a lot going on my screen. Let me minimize some things. More time. Okay, so if I take my 2 pi over 3 plus 2 sine 2 pi, so this is f of 2 pi over 3. 2 pi over 3 doesn't simplify, but what is the sine of 2 pi over 3? Yeah, it's the square root of 3 over 2 business, isn't it? Is it positive or negative?
Positive.
It's positive because I'm in quadrant 2. So this is actually 2 pi over 3 plus 2, and then it's square root 3 over 2. So what do you see happen? The 2's cancel. That's kind of nice. So my y value, as ugly as it is 2 pi over 3 plus square root of 3. If you want to get a common denominator, you could, but I don't know that that actually makes it any better. It's just as ugly either way. So that would be our maximum value. Whoops. And then we're going to do the same thing by plugging in 4 pi over 3 to get our minimum value. So this is a maximum value of 2 pi over 3 plus square root 3. And then if I do 4 pi over 3, what happens? It's close. What is the sign of 4 pi over 3, though, instead? It's actually negative. So instead of having a positive here, I have, these are 4 pi's, I have a negative right here. So I end up getting a subtraction sign right here. So I have 4 pi over 3 minus square root of 3. Yuck. Yuck. A graph. You said that it was weird looking, Kaylee. Is that what you said? Okay, so let me sketch for you what I have drawn on here. Did you only look between 0 and 2 pi? Out of curiosity?
That shows the entire thing, but I'm looking at.
Okay, good. So I'm just going to draw the part between 0 and 2 pi. If you want to change the window of your screen to only include that part, you can. But it looks kind of like that. Does that look okay? I mean, roughly speaking, it almost looks like a cubic function. And sure enough, we see that we have a maximum here. We have a minimum here, right? So this maximum is occurring at 2 pi over 3. The minimum is occurring at 4 pi over 3. That's 2 pi over here. And it's increasing, and then it's decreasing, and it's increasing. Any questions on that one?